Hello, good morning, good afternoon, and good evening. On behalf of PioPetro and Millet Research Hub, I'd like to welcome you all in our third session of the summer internship program. My name is Mayar Tore, a senior gas and petrochemicals engineering student, SPE Egypt Young Professionals member, and I'll be your moderator for today. So before we start, please keep the chat box professional and ethical, and don't forget to drop your questions in the Q&A section below. So without further ado, let's welcome Dr. Ahmed Algarhy, who will give us a session on hydraulic fracturing operations and earth modeling. Dr. Ahmed Algarhy is a distinguished professional with over 20 years of experience in the energy and petroleum industry. Specializing in production enhancement services, Dr. Ahmed's expertise includes acidizing, hydraulic fracturing, geomechanics, geothermal energy, carbon capture, utilization and storage, and hydrogen technologies. He has successfully led projects for major companies like Apache, Chevron, BP, Shell, and Total. Currently, Dr. Ahmed, a research manager at Millet Research Hub, Dr. Ahmed has a proven track record in publishing research on machine learning applications in energy. His academic tenure as an assistant professor at Merida College underscores his deep knowledge in production enhancement, petrophysics, and well logging analysis. Dr. Ahmed holds a PhD and master's in petroleum engineering from Texas Tech University, has published over 30 research papers, and received the Distinguished Achievement Award from SPE International in 2021. Now let's give a warm welcome to Dr. Ahmed. Thank you so much, Dr. Ahmed, for coming today, and the mic is yours.
Mayar, thank you very much for the nice introduction. Today we'll have the second lecture in our course, Introduction to Hydraulic Fracturing. And as we know, this is part of the summer training of PioPetro and Millet Research Hub. I received some good questions written below the video of the first lecture on YouTube. One of you asked why we need to keep the injection rate constant. Why we need to keep the injection rate constant. In the first lecture, I mentioned it is better to do our best to keep the injection rate constant. And I said, if you want to know why, please ask me at the end of the lecture. So I was planning to explain this by details in the third lecture, which is the coming Tuesday. But quickly, I can tell you the mathematical model we developed to evaluate hydraulic fracturing after we do the job, to calculate or to get an estimate for the closure pressure, for the leak off, all these things, we have an assumption in our mathematical model that the injection rate is constant. So if you fail to keep the injection rate constant, it means the mathematical model you are using to calculate the closure pressure and the leak off will be wrong and will not give you a result make sense. Okay, so I want to keep the injection rate constant because this is one of the assumptions we made when we developed a mathematical model to predict the closure pressure and leak off coefficient or the leak off behavior in general. Okay, and I will explain this more on the coming Tuesday. Okay, so today I'm planning to talk about operations and mechanical earth modeling. So some of mechanics related to hydraulic fracturing. So let's begin. The lecture today, we will talk about the equipments we use in hydraulic fracturing. Also, we'll talk about the materials we are using in hydraulic fracturing. And I will introduce what is principal stresses. And finally, we will talk about mechanical earth modeling. Okay? So before I start talking about operations and the equipment we are using, I wanted to differentiate between two things. There is a conventional hydraulic fracturing we used to do in Egypt, in Iraq, in Algeria, in Saudi, in India, and China, everywhere. Okay, we call it conventional hydraulic fracturing. And this is when we frack a conventional reservoir like sandstone formation, for example. Most likely, I will have a vertical well or slanted well, sometimes a horizontal well, and I will inject cross-linked gel, something like jello. But this frac fluid, which is the jello we are injecting, we call it cross-linked gel, and I will show you a video for that, is totally different with the frac fluid we are using with shale. When we frac shale, most likely we use something called slick water. So the slick water, simply it is uh, just a fresh water with friction reducer and some little additive. Okay, and Dr. Ahmed Gom'a will explain this more in his lecture because he will give you a lecture about frac fluids. Okay, so let's go back to conventional fracking. Let's assume we have a sandstone reservoir and we want to frack it to improve or to enhance productivity. I have a well and that will produce, let's say, 500 barrels of oil, and I want to double this number. I want to make it 1,000. I want to make it 800. So one of the recommendations I get is, why don't you hydraulic frac this well? Okay. So in this picture, you see the equipments we are using. Look to the mouse, please. Look to the mouse, please. Okay. You will see two rows of big trucks. See, this is one row. And here is a second row. And there is some tubes in the middle here. And there is a big equipment in one side here. I will tell you the names of everything. Just wait a few seconds. Okay. So these two rows are pumps. Each big truck of these is a pump. We sometimes call it triplex pump based on the type of the mechanical type of that pump. And this pump may be 2,000 horsepower, maybe 1,600 horsepower, maybe 2,300 horsepower. But in average, we can say roughly it is something like 2,000 horsepower. Okay? So if you want to measure how many horsepower we are using in this operation, you can count how many pumps in the location. 1, 2, 3, 4, 5, 6, 7. And in the other side, there is 7 like them. So we have 14 pumps. Let's say we are using 12 of them and we have 2 as a backup, or we are using 13 of them and we have 1 as a backup. So we have on average something like 26,000 horsepower, assuming I'm using 13 pumps. But if the pump is 2,000 horsepower, I will not use all of that. Most likely during the operation, if it is 2,000, I will use, let's say, 1,500. I will not take it to the maximum. So you can multiply 1,500 horsepower times 13 pumps I'm using, then you can calculate how many horsepower you are using. Okay? If you have an operation and you are using more than 20,000 horsepower, this is a big job. In Egypt or in Saudi or in Kuwait, most likely the job is like a 10,000 horsepower. I need just 5 pumps, 6 pumps, 7 pumps, and that's it. Okay, so this is comparing this job with what we have in the Middle East. This is like a big one. Okay, so these two rows, I told you these are pumps. And for sure, whenever you see this red color, what is the company running this job? Write me in the chat. Write me in the chat. What is this company? Most likely Halliburton, yes. Whenever you see this color, most likely it is Halliburton. Okay, especially when you zoom in and this monitoring track, or you will see the name of the company. Okay, what we have in the middle, these pipes, we call it manifold. We call it manifold. So I have two rows of pumps, and in the middle we have a manifold. Okay, in this side I have something we call blender, and the blender, this is the heart of the operation. I will use the blender to mix the frac fluid with the chemicals, with proppant. Then after I mix them, I send them through the manifold to the pump. The manifold has two levels. One level, we call it low pressure part. Then the low pressure pipes will take the frac fluid, mix it with proppant, with chemicals, with everything from the blender, take it to the pump, then the pump return it back to the manifold as a high pressure. Then the high pressure line will go to the wellhead. The wellhead is here. Look to the mouse, here is the wellhead. Okay, so the manifold has pipes low pressure and has another pipes high pressure. How you know them? The low pressure pipe, you will see the hoses we are using to connect the blender with the manifold. You will find it rubber, made of strong rubber. It means this is low pressure. But the pipes connecting the pumps with the manifold that has high pressure, you will find it steel pipe. So whenever you look, is it a steel pipe? It means high pressure. Is it a rubber tube or a rubber hose? This is low pressure. Okay? You will see a lot of tanks here behind. These tanks, maybe for water. Sometimes we have a big open bed for water. Sometimes we put the water in tanks. Okay, so these tanks maybe for the water, maybe for the sand, maybe for the chemical, things like that. Okay, and you will have something here called the monitoring truck. Look to the mouse, this white van. We call it monitoring truck. Sometimes we call it control truck. Sometimes we call it data van based on the company. Each company give it a different nickname. But this monitoring truck, you will find the job supervisor. You will find the frac engineer, maybe the company man, maybe maybe the fluid tech, the guy who go get samples from the frac fluid and do quick testing in a small lab inside this truck and confirms that we are meeting the recipe, we are meeting the properties we were planning to have for this frac fluid. Okay, and the job of the team inside this monitoring truck is to monitor and supervise the job. They have a radio, like microphones. They are talking to the team in the location, and the supervisor can tell the team when to start pumping, when to stop pumping, when to change from a stage to a next stage, and so on. Okay. So we talked about pumps, we talked about tanks, we talked about the manifold. There is something called frac head. I told you here is the wellbore, the Christmas tree, and we have the frac head here at the top of the Christmas tree here. What is connecting the manifold with the Christmas tree so we can inject the frac fluid and the proppant. Okay? There is something we call tree saver. Tree here means a Christmas tree. The tree saver, I will use it to protect my Christmas tree. This Christmas tree, for example, rated as 5K. It can handle up to 5,000 psi pressure. But the surface pressure in this job may reach 7,000 or 8,000 or 9,000. So how the Christmas tree can handle 8,000 psi and it is rated for a maximum pressure of 5,000? And for sure, if it is 5,000, if it is 5K, 5K means 5,000. Okay? For safety, I will not use it above 350, 3,050. Sorry, 3,500. I will not use it above 3,500 or maybe 4,000 maximum. Why? For safety reason. We don't want to get any accident in the location. Okay, so how I can use this Christmas tree to handle injection pressure, surface pressure of 8,000 if the Christmas tree not ready for that. I will use something called tree saver. It is a long tube, and I will open all the valves of the Christmas tree, and I will put this tube, the tree saver, from the middle, from the top. Then it has two rubber cups will seal below the casing hanger. And this tube, this tree saver, can handle up to 10,000 or 12,000 based on its type. So I will use a tree saver to avoid changing the Christmas tree during the job, because during the production, the surface pressure will not exceed 2,000 psi. So why I go and buy expensive Christmas tree that can handle 8,000 psi or 2,000 or 10,000 psi? There is no need for that. Okay, I hope the basic idea of having tree saver is clear. Sometimes we call it isolator. Okay. I used to ask my students, do you see a workover rig? There is no workover rig here. You see a crane. So we call this job rigless operation. Rigless means there is no workover rig in the location. Okay. And also I ask my students, do you see where's the wellhead? Here is the wellhead. Easily you can find the wellhead. Look to the two rows of the pumps. Look to the blender. And in the other side, you will see the wellhead. And the manifold for sure will be in the middle. Okay. Here is a workover rig. A workover rig is like similar to a drilling rig, but is smaller. One stand of a workover rig, most likely two tubes, two pipes connected together. This is one stand. If you have a drilling rig, one stand will be three pipes. If it is big one for offshore, maybe you will find it one stand is four drilling pipes. But in general, most likely drilling rigs, the one stand is three drilling pipes. But for workover, it is only two. This is how I used to look like 11 years ago when I was a frac engineer for Khalda Apache in Egypt. Behind me, there is a lot of pumps, and here is a manifold. And for sure, whenever you see the steel pipes, it has high pressure. For sure, I get this picture before starting the job, so it was safe environment. During the job, we cannot take pictures like this. It is not safe. Okay. Now I will talk about hydraulic fracturing materials, the materials we are using. And as I mentioned, Dr. Ahmed Gom'a is a PhD from Texas A&M and worked long time for Baker Hughes, and now he's working for British Petroleum, for BP, and he is expert in frac fluid. So he will kill it. He will explain it by all details, and you will enjoy his lecture very much. Okay. So this is also a picture for a big job. This is a different company for sure. It is silver, not red anymore. And again, you can count 1, 2, 3, 4, 5, 6, 7, 8. 8 trucks, and the other side there's 8 trucks. So this is like a 16 trucks if each one is 2,000. So this is like a 32,000 horsepower ready in the location. But for sure, I will not use all of them because I need to have one or two as a backup pumps. Also, I will not use the pumps to the maximum value. If it can handle 2,000, I will use it. I will run it, let's say, for 1,600 or 1,500 or something like that. Okay. This is also a Rigless operation. You see the crane here, and here is the wellhead. On the other side, for sure, you will see the blender. And in the back, you will see tanks for sand and chemicals. Most likely, they get water from, they have a big open bed and they put a lot of fresh water in it and they get the water from it, not from the tank. So these tanks, most likely, you will find it for sand. Sand means proppant. And hydraulic fracturing, when we say sand, it means proppant. And I will explain what is proppant very soon. Okay? And the monitoring truck should be here. This is the monitoring truck. If you look at the mouse, this is the monitoring truck. By the way, the monitoring truck must be in a location that easily you can see the wellhead. By the way, I don't like this location for the monitoring truck. Do you know why? Because I see the crane in the middle, and if you look from the monitoring truck window, maybe you will not see clearly the wellhead. The monitoring truck should be in a location like here. Look to the mouse location, should be here. When you look from the window, you need to see the wellhead very clear. Why? Because if there's any accident happen, you need to see all the location. So this will give you better communication with the team, especially if there is any kind of accident happen. You need to stop the operation immediately. Okay. So for sure, we use a lot of fresh water, and we use a lot of KCl, the salt. You know, the salt we are eating is sodium chloride, and this is potassium chloride. So what we use in hydraulic fracturing, in the conventional hydraulic fracturing, is KCl. Also, we use it in tilling fluid or workover fluids. So KCl, this salt, we use it a lot. And mainly we use it to inhibit clay swelling. Okay. We will use a lot of guar, and guar is something similar to beans. And when we grind it, it will become something like starch. When we mix it with water, it will make something like a milky shape, like something like milk. Okay. When you add to it something we call cross-linker, it will become like jello. It will become like jello. Okay. Also, I will use a lot of proppant, and proppant, this is, we call it sand, and proppant is small balls we injected with the frac fluid. So when you stop pumping, the fracture will try to close. So the proppant will keep it open. The proppant will be in the middle. So the proppant will not let fractures to close. So I can keep the improvement I did for the conductivity of that formation. So the formation will be very conductive because of the fractures and the proppant I injected. I will use a lot of chemical like cross-linkers, breakers, and I will show you a long list of chemicals in the next slide. Here is Dr. Ahmed Gom'a, and he will teach you 2 lectures, one about matrix acidizing and a second lecture about frac fluids. Okay? So the fracturing fluids in general, the conventional fracturing fluids in general, more than 90% of it is just water, fresh water. If you live in a country and you don't have a lot of fresh water, maybe you cannot frack a lot of wells. If you live in Libya, for example, or if you live in Algeria, for example, and there is a big reserve of oil shale in Libya, for example, and big reserve of shale gas in Algeria and shale oil in Libya, but there is not enough fresh water in Algeria. There is not enough fresh water in Libya to frack these shale plays. Also, there is no fresh water in Egypt. So in Egypt, we have the Nile, the River Nile, but it's still not enough to do massive activities of hydraulic fracturing for shale in the Western Desert in Egypt. So this is one of the big challenges that when we develop shale, we need to use a lot of fresh water. In the United States, there is huge amount of fresh water. It rains all the year and there's big lakes. So there's no problem in fresh water in the United States. There's no problem in fresh water in China and in Argentina. This is why these three countries are working heavily in shale. Okay? So more than 90% water, about 9% sand, which is proppant, and less than 0.5% is chemicals. These chemicals may be surfactant, maybe KCl, maybe gelling agent, maybe scale inhibitors, maybe pH adjusting agent, maybe breaker, maybe crosslinker, maybe ion control, maybe corrosion inhibitor, maybe biocide, maybe acid, maybe friction reducer. So it is complex recipe. It is complex recipe, and there is a lot of science behind having good frac fluid. And I believe Dr. Gom'a will explain these things by detail, and we'll learn a lot from him. Look to this picture. Look to the mouse. This is something like milk, right? How we get that? We get it from this bean. This beans, we call it guar. We plant the guar in India and neighbor countries to India. So India, Bangladesh, Pakistan, all these countries are a good place to plant guar. And again, it is similar to beans, and it is a good business there. You can make a lot of money if you are planting this guar, because it is not only used in hydraulic fracturing, we use it a lot in food, in manufacturing food. So if you go to buy a lot of foods for kids, cookies or any kind of sweets, and you check the ingredients, most likely you will find guar part of it. Okay? So here is the beans. We grind it. We make it like a powder, very similar to starch. We mix it with water. It makes this thing similar to milk. If you add crosslinker to it, it will be like this picture, like jello. Crosslinker gel of the crosslinker will make the molecules stick together and make longer and longer and longer molecules. It become polymer. Okay, it will become something like jello. Okay, please watch this video.
Nice.
This is a frac fluid, and this guy's job, we call it fluid tech. The technician work with the frac team in the location to confirm that they are making the frac fluid the right way. This frac fluid we are using in the Middle East and India and many other countries and Africa, for example. But in the United States, because most of the activities we are fracking shale, so we use something else called slick water, and slick water is just water and friction reducer, so it is not that jello. It is light fluid. Okay. After you pump the frac fluid and you fracture the formation, you will crack the formation the same like this picture in the bottom here. Okay. But when you stop pumping, the fracture will close again because you are applying a pressure and that pressure exceeded the resistance of the formation and you parted the formation. Now the formation is broken. You have a crack in the formation, but when you stop pumping, these fractures will close because there is stresses in the earth and these stresses will close these fractures again. Right? This is the function of proppant to keep fracture open. I will use proppant to keep fracture open after I stop pumping. You will have different shapes of proppant and different sizes. Different shapes and different size. See, we call this size 4070. It is a very small. This is 3050. This is 2040. This one is 1630. So different sizes. And you see, whenever we have a big number like 4070, the proppant become smaller. Actually, 4070, it means a range for two sieves. A sieve, this is what you see in the picture in the middle. This is what we call a sieve. Okay? And this number, this is the number of how many holes per 1 square inch. So 1 inch square, including, has 40 holes. And I have a second sieve, and 1 inch square has 70 holes. So the one that has 70 holes, for sure, the holes are smaller. Right? So the proppant can go through the sieve that has 70 holes per 1 inch square. Sorry, it can go through the one that has 40 holes in 1 inch square and cannot go through the one that has 70 holes, which is the smaller one. So I will have a range. So 40, 70, this is a range of proppant size. What about 2040? I have two sieves. One sieve has 20 holes in 1 inch square, which is big holes. So the proppant can go through it and cannot go through a sieve that has 40 holes in 1 inch square. So this is proppant 2040. Is it clear? I hope so. Okay. So what is a proppant used for? We use proppant to keep fracture open after we stop pumping. Why different in sizes? Because the fractures we are having has different opening mouths. So the width of the fracture will be different. If I have a very narrow fracture, the fracture is very tiny, very narrow, I need to use a very small proppant. And this is, I need to know exactly the mechanical properties of the formation, especially the Young's modulus. If I have a high Young's modulus, let's say 10 million psi Young's modulus or 8 million psi Young's modulus, I'm expecting a narrow fractures, for example. So I will recommend smaller proppant. And the proppant itself, most likely it needs to be 6 times smaller. The diameter of one proppant should be 6 times smaller than the opening of the fracture. So most likely when we do modeling, we model it like this: 6 times or less smaller than the opening of the fracture. Okay? Think about the proppant size and Young's modulus. I already answered this. I told you whenever we have higher Young's modulus, I need to use smaller proppant. Okay. Also think about the the proppant strengths. The proppant strengths. If we have minimum horizontal stress, let's say 7,000 psi, and maximum horizontal stress 8,000 psi, and overburden 10,000 psi, for example. Okay, and I have a proppant will be crushed when you apply 5,000 psi on it. It means this is not a good proppant. This proppant, if you inject it, will get crushed inside the formation and it become like a powder and it will plug the fractures you made. Very bad choice. So you need to select a proppant can resist the stresses in the formation and can stay in a good shape without any crushing for a long period of time. So you need to apply a crushability test for the proppant you are using and be sure that this proppant can handle the high stresses or the stresses in that formation without getting crushed. Okay, now I will introduce the principal stresses. What is principal stresses? And we'll talk a little bit about some rock mechanics basics. Why this is important for us as a petroleum engineers? We drill horizontal wells and we need to know what should be the best direction for the horizontal section. We drill the horizontal section with the minimum horizontal stress direction or with the maximum horizontal stress direction. Which one is better? Okay. Also, I want to know if I will hydraulic fracture a horizontal well, the fracture will grow to which direction? So these directions of the optimum horizontal well direction or the optimum hydraulic fracturing direction, I relate this to the direction of the minimum and maximum, and we'll see which one is better now. I mean, after this slide. So first, let me introduce what is principal stresses. There is a lot of stresses inside the Earth. We are drilling, and we can summarize the stresses in the reservoir or in the Earth we are drilling into 3 principal stresses. They have 90-degree with each other. So think about something like X, Y, and Z, and one of them is vertical because one of them is the overburden. Overburden is the weight of the rock, and this weight of the rock the weight will be perpendicular or pointing to the center of the Earth. The same like the weight of your body. If I'm asking you how weight you are, how what is your weight, you may tell me you are 80 kilogram, 70 kilogram, 65 kilogram, 75 kilogram, for example. Okay. If I will ask you what is the direction of your weight, because of gravity, your weight will point to the center of Earth. Right? So overburden is the weight of the rock at a specific depth. So we know its direction. It must be pointing to the center of the Earth. Right? How to get the magnitude of the overburden? You can integrate the density log. When you get a class in well logging, you will get something called density log. And each 1 foot or each half foot I will measure the density of the rock. I can integrate these densities and get the weight and keep adding this weight together so I can get the weight at a specific depth, and at that depth, I will say the weight of the rock at that depth, this is the overburden stress magnitude. This is the value. And the direction is pointing to the center of the earth because it is weight. Okay? And I have two horizontal stresses. Most likely they don't have the same magnitude. One of them will be a little bit bigger. The bigger one, I will call it the maximum horizontal stress. And the smaller one, I will call it the minimum horizontal stress. So assuming I have a normal fault system, I have a fault here. If you get a class in geology, you will understand this part easily. And you see the right side of the fault will slid downward, will move down. Why it is moving down? Because the overburden magnitude is greater than the minimum and the maximum horizontal stress. So the faulting system here, we will call it normal faulting system. I will have a crack and the right part of the rock will move downward. Okay? If I have a fault and the minimum horizontal stress magnitude and the maximum horizontal stress magnitude, both of them greater than the overburden magnitude, the movement of the fault will be upward. The right side will move upward. Why? Because the horizontal stresses are bigger and it will keep carrying the right part of the rock and pushing it up. So I know that in this case, the overburden is the smallest in magnitude. Okay? I will call this thrust fault or reverse fault. Why reverse? Because this is the opposite of the normal fault. What about if you have the overburden magnitude, not the largest and not the smallest, just in between the magnitude of the minimum horizontal stress and the maximum horizontal stress? So the movement will be, the two parts will move parallel to each other. We call it strike slip fault. Strike slip fault. So these three different fault system. This is for sure there is more types, more faulting systems, 6 or 7. But this is the most common three. And this is enough to explain what is overburden, what is maximum horizontal stress, what is minimum horizontal stress. Okay? So for each one of these three stresses, I need to know two things. I need to know the magnitude. I need to know the direction. Why? Because it is a vector. Guys, let me ask you this question in the chat. What is the difference between pressure and stress? Write me in the chat. What is the difference between pressure and stress? Write me in the chat the difference between pressure and stress. Thank you very much. I get a perfect answer at the beginning. Who's this guy? Let me get his name. Arnai Roy. Thank you very much. Pressure is scalar. Stress is a vector. This is the right answer. So we measure pressure by PSI, pound per square inch, per inch square, PSI. And we measure stress also by PSI. So what is the difference? Pressure is a scalar. When you talk about pressure, I need to know exactly the magnitude. That's it. I don't care about the direction. Because it is a scalar value, I don't care about the direction. I care only about the magnitude, the value. And most likely I will use pressure for fluids, like liquids, gases. But the stresses, most likely we use it with solids. But what is very important for stresses is it is a vector. It needs two things. It needs a magnitude, a value, and needs a direction. Magnitude and direction, we call it vector. So stress is a vector. Pressure is scalar. And we measure both of them using the same unit, which is PSI. So for each one of the minimum of the principal stresses, the three principal stresses, I need to know the direction and I need to know the magnitude. Okay, so to get the direction of the minimum and maximum horizontal stress, we agreed that the overburden is so easy. We know the direction, it is pointing to the center of the earth. We know the magnitude, just go and integrate the density log you have. So I will focus now talking about the minimum and maximum horizontal stress, because this is my challenge now. So to get the direction, I can use dipole sonic. I can use a dipole sonic log to get the direction of the minimum and maximum horizontal stress. I can use the caliper log. I can use the image log, the FMI. I can use a website called World Stress Map. You enter the location and they will give you a map like the one you have it in the middle here. And it will show you all the faults near the region. And from the direction of the fault, you can get an idea about the direction of the minimum and maximum horizontal stress. Also, I can do something called failure analysis. You can see the breakdown and collapse in a well bore. And this is very helpful to get the magnitude of the maximum horizontal stress, because it is very difficult and complicated to get the magnitude for maximum horizontal stress. To get the magnitude for minimum, or a good estimate for the minimum horizontal stress, is so easy, and there's a lot of different ways. But to get a good estimate for the maximum horizontal stress, it is very, very complex and challenging. Okay? Look to this picture. This is a well bore, and we use this during drilling. If the mud weight or mud pressure very low, you will get collapse. You'll get break out. And the break out, look to the second picture from the left. If you make a line on the two red things here, this is the direction of the minimum horizontal stress. This is the direction of the minimum horizontal stress. If you keep increasing the mud pressure or the mud weight, you will fracture the well bore. You will get lost circulation. You will fracture the well bore. And this fracture will be perpendicular to the minimum horizontal stress direction. I like to say perpendicular to the minimum horizontal stress. This is more accurate than saying with the direction of the maximum horizontal stress. Okay? So it is better to say the hydraulic fracturing go in a direction perpendicular to the minimum stress. Okay? And in the left, you see this is a caliper log, and here's a trajectory, and here's the surface casing, here's the second case, and in this well, we have 4 casing, not 3. We have 4 level. And whenever you see it to the caliper log, you can get an idea about the location that we have a lot of break out. So you can get an idea about, using the caliper, you can get an idea about the direction of the minimum and maximum too. It is better if you have a lot of this information available to do it using different ways, so you can confirm exactly the direction of the minimum and maximum. It is better to use different ways to confirm the direction of both minimum and maximum horizontal stress. If you get one of them 90 degree, this is the second. This is the other one. Please answer this question in the chat. Which one will be better in production? If you drill a horizontal well with the direction of the maximum horizontal stress, like the first one to the right, and you drill the second one with the direction of the minimum horizontal stress, which one will produce more? The one you drill with the minimum horizontal stress, or the one you will drill with the maximum? Okay. So most of you get it right. So whenever we drill the horizontal well, or the horizontal section, or the lateral, with the direction of the minimum horizontal stress, this will give you more production, better production. Why? Because when you do multi-stage fracturing, the fractures will be perpendicular to that direction, so you will get nice fractures like this. You can get as many as possible. You can make 20 fractures, 100, whatever you want. And when you frac this way, you will get more contact with the reservoir, so you can produce more. Okay? So which one? So I will call, look to the mouse. So the well to the right, I will call it 1. The well to the left, I will call it 2. So this is 1 and this is 2. Which one is easier to drill, 1 or 2? Which one is easier to drill? Drill well 1 or 2? Some of you get it right, some of you get it wrong. So please remember this. Well number 1, the one to the right, I can drill it easier. The rate of penetration will be faster and higher because I'm drilling, I'm pushing against the minimum horizontal stress. I'm going in a direction perpendicular to the minimum, so I'm pushing against it. So it will be easier to drill, but drilling is just 2 weeks, 3 weeks of the well life. Okay, so if I'm drill well number 2 with the direction of the minimum horizontal stress, and I can handle some problem. Let's say I will get delay 1 or 2 days extra, for example, to drill it that way. But the production time of that well will be 10 years or 15 years or 20 years. So if you compare 20 years of production, of better production, with 1 or 2 days or 1 week more in drilling, it is nothing. So even we know that drilling with the direction of maximum horizontal stress will be easier, but we prefer to drill horizontal wells with the direction of the minimum horizontal stress, because later we will frag these laterals and we will get better production. Okay. Here's the same thing. I will drill the horizontal well with the direction of the minimum horizontal stress, and this is what we do every well. Finally, I will talk about some mechanical properties, and I will continue on Tuesday talking about mechanical issue model. I will try to finish quickly, so I will give you more time to ask questions. So there is a company called GMI. GMI, it is a company founded by Dr. Mark Zuback and Dr. Dan Moose long time ago. Mark Zuback is maybe the most famous guy working in geomechanics. He's a professor at Stanford University. He already retired. And Dan Moose was one of his students. And they established a company called GMI. Okay, Geomechanics International. Later, Baker Hughes bought that company. So GMI now is part of Baker Hughes. Okay. So to calculate the vertical stress, to measure the vertical stress, the overburden, you can integrate the density log, as I told you. To get the pore pressure, you can use RFT or DST, or there's a lot of ways to do that. To get estimate for least principal stress, which is, if it is normal faulting system, it will be the minimum horizontal stress. I can do leak of test or extended leak of test or mini frac, or I can, check the loss circulation or ballooning. All these things can give you an idea about a good estimate for the least principal stress. For the maximum horizontal stress, I need to do something called wellbore failure analysis. And this technique developed by Dr. Dan Moose long time ago. It was his PhD at Stanford University, like maybe 30 years ago, or maybe 40 years ago. And what I can tell you, this technique also very complex, not easy to do, because you need a lot of data, a lot of failure data, wellbore failure data in the same location, let's say hundreds of wells or tens of wells, and we most likely will not have this information. So it is a good technique, but most likely needs a lot of input. So most likely you will not have this input, so you cannot apply it. So we used to give some estimate, or what we call it, like some estimates, like I will assume the maximum horizontal stress is 1.1 minimum horizontal stress, or 1.2 minimum horizontal stress, or 1.3, something like that. So we call it like a sensitivity study. We do some sensitivity to get a good estimate for maximum horizontal stress. And for rock strength, you need to take course and take it to the rock mechanic lab and do some tests there. So I will use a lot Poisson's ratio and Young's modulus and minimum horizontal stress. So Poisson's ratio, simply, it is a lateral strain over the longitudinal strain. Look to this cylinder shape. When you apply a force from the top and the bottom, apply stress from the top and bottom, okay? So the length of the cylinder will change, and the diameter of the cylinder will change. When you divide the lateral strain over the longitudinal strain, you will get something called Poisson's ratio. Poisson, this is a name of a French scientist, lived in the 18th century. He was a very famous French scientist at that time. Okay? And the Poisson's ratio value must be something between 0 and 0.5. Remember this, must be between 0 and 0.5. If someone told you Poisson's ratio is 0.7 or 0.8, it means there is something wrong. Don't talk to this guy again. He didn't know what he's talking about. So it must be something between 0 and 0.5. This is the range of Poisson's ratio. Okay? I can use this equation to calculate the minimum, or to estimate the minimum horizontal stress. Nu, this is not V, this is nu, the Greek letter nu, and nu, it is the Poisson's ratio. Nu over 1 minus nu, and here is the sigma V, this is the overburden, minus alpha PO. PO, this is the pore pressure, and alpha, this is something called, we call it bio constant. Bio, also a name of a scientist, French scientist. And bio constant most likely to be something less than 1. So let's say 0.7, 0.8, 0.9, 1. And most likely they will provide this value to you. They do some lab testing, and they will provide this value to you. Okay? And sigma T at the end, this is something component, we call it tectonic stress. And most likely an expert will give you an estimate for that value too. So this equation can give you a good estimate for minimum horizontal stress. Or you can go ahead and just do well testing. You can do many frac tests, or we check the extended leak of test or the leak of test you have during drilling, and we can get a good estimate for that. Here is the Young's modulus. The Young's modulus, when you apply stress on a material and you get a strain, and you keep recording when you change the stress, how much strain you get, and keep changing stress, get 10 values for, let's say, applying different stresses, and get the strain, you can draw this shape. So you can keep doing this until the material get broken and fail. get fractured. So when you divide the stress, when you get the stress over strain, we call this Young's modulus. So Young's modulus is stress over strain. Strain is unitless. Strain has no unit because it is a length over a length, a length over a length, millimeter over millimeter, or centimeter over centimeter. So it is unitless. They will cancel out. Okay? So the unit we use for Young's modulus, it is the same unit we use for stress. So Young's modulus, we measure it by PSI, the same unit we use for stress. Okay? We have a big problem in hydraulic fracturing, not only in hydraulic fracturing, in any rock mechanics project or geomechanics project we are doing, and we need to do mechanical earth model. We have something we call dynamic Young's modulus and static Young's modulus. In oil and gas business, most likely you will have the sonic log, the compressional wave, and the shear wave, and from them you will get Poisson's ratio, and you will get Young's modulus, dynamic Young's modulus. Okay, so the dynamic Young's modulus you are getting from the sonic, I would call it dynamic Young's modulus. But this is not the Young's modulus I need to have in my hydraulic fracturing design. When I design for a hydraulic frac job, I need the static Young's modulus, the value I receive from the rock mechanic lab when I give them cores from my formation. Then they do the testing in the lab and they give me the report. Hey, here is your Young's modulus. To the one I get from the rock mechanic lab, when they do the triaxial test on cores, we call this static Young's modulus. But most likely you will not have this. This is very expensive, and most likely they will not core most of the wells you are working on. So you will have the sonic log, and you will get only the dynamic Young's modulus. Before finishing your work or to do your work, your frag design, you need to convert the dynamic Young's modulus into static Young's modulus. You will find hundreds or maybe thousands of different equations to convert dynamic to static. I listed here maybe 17 or 25 different equations to convert dynamic to static Young's modulus. Which one of them is right? I believe all of them are wrong. Why? You need to develop your own local correlation for the field you are working on or for the area you are working on. You need to develop your own local correlation to convert dynamic to static Young's modulus so you can get something you can trust. Maybe you have your company cored some wells in the area. This will be very valuable for you, so you can use these values. Or maybe a neighbor company working in the same area, they published a paper and they cored some wells and they published the estimates they get for static Young's modulus. Okay, but anyway, you need to convert dynamic Young's, you need to find a good way to convert dynamic Young's modulus to static Young's modulus. And you need some experience to do it right. So please, when a project like this assigned to you, you need to talk to an expert in your company, like a supervisor, so he can guide you what should be the right correlation to use to convert dynamic to static Young's modulus. It is very complicated. You will get a lot of headache when you work on that. But anyway, whenever you get some experience, you will know how to handle this. Okay. Are you ready? I have some questions for you. Let me check how to start. Guys, there's 5 questions. Please go ahead and answer them. So you should see 5 questions in your screen. Please go ahead and answer them. I will give you like a minute, then I will start answering the questions with you. Okay, so I will end the poll now, and let me answer the questions with you. So the first question: what is the primary cause of formation damage in petroleum reservoirs? A, excessive oil production, drilling and completion operations, high reservoir pressure. D, natural gas injection. What do you think? What should be the right one? So the first source of formation damage is drilling operations, drilling and completion operations. This is the most important reason for formation damage. So the right answer is B, drilling and completion operations. Question number 2, which of the following is a common method to mitigate formation damage? A, increasing production rates. B, hydraulic fracturing. C, acidizing. D, using heavier drilling fluids. The right answer is acidizing. Guys, hydraulic fracturing not fixing the formation damage. Hydraulic fracturing bypassing the formation damage. It is different. Bypassing the formation damage means we are creating a new highway, but the formation damage will stay as it is. But acidizing, when we use acids or acid treatments, most likely we do this to dissolve the formation damage. So acidizing, we do it to remove the formation damage. Question number 3. In hydraulic fracturing, what is the purpose of using proppants? I told you, proppants, we use it to keep the fracture open. To increase fluid viscosity? No. To prevent the fracture from closing? Yes. To reduce formation pressure? No. To seal the well bore? No. So the right answer is to prevent the fracture from closing. Question number 4. Which type of acid is commonly used in acidizing treatment to remove formation damage caused by carbonate scale. I know that we did not explain this before, but remember the most famous acid we use is HCl. Especially I have a carbonate scale, so HCl can dissolve carbonate. So hydrochloric acid, this is the acid we are using. Okay, so the other choices, sulfuric acid, acetic acid, nitric acid. HCl is the most common one for carbonate scales. Question number 5 and the last question. What is the primary goal of hydraulic fracturing in unconventional reservoirs? Unconventional reservoirs like shale gas, shale oil, like tight sands, like coal bed methane, very tight carbonate. If the permeability very, very, very small and we measure it by nano, we call this unconventional. Okay. Choice number A, to increase water production, to enhance oil and gas recovery by creating fractures that increase permeability, to reduce the porosity of the rock, to stabilize the wellbore. The right answer is to enhance oil and gas recovery by creating fractures that increase permeability. Guys, there is a mistake in this question. It is not right to say to increase the permeability. I'm increasing the conductivity of the formation, not increasing the permeability. In hydraulic fracturing, I am not increasing the permeability of the formation. The proppant has higher permeability, and because of the proppant and the fractures, I am increasing the conductivity of the formation. Okay, so please correct that. Okay, so that's it for today. I will check if there is any questions I can answer. I can take one of the questions, then we can close. So I will take just one question. So if I have youngest modulus on already well processed, it's static youngest modulus. No. The youngest modulus you get from the sonic log, this is dynamic. Why dynamic? Because I use the sonic wave, and the sonic wave has high frequency and small magnitude. We call this dynamic youngest modulus. But when you do the triaxial test in the rock mechanic lab, you apply high magnitude and small frequency. This is the opposite. And this is similar to what we do in the real hydraulic fracturing. So what we need to have to design a hydraulic fracture job is a static youngest modulus. But unfortunately, most likely you will have only the dynamic youngest modulus because you have the sonic log and you don't have cores, and you don't have a report from the mechanic lab after testing these cores. So most likely you will have the dynamic youngest modulus, and you need to complete your design. You need to find a way to convert dynamic to static youngest modulus. Okay. Thank you very much. We will continue talking about hydraulic fracturing on Tuesday. Please, if you have any questions I did not answer today, write it below the video on YouTube. I go to the YouTube video after we post it, and I read all the questions below the YouTube video. So please, if you have any questions we did not answer today, leave me that question under the YouTube video. Thank you very much, and see you Tuesday.